You are watching the Control Design educational video series, Automation Basics, Industrial Networking. This video has been brought to you by our sponsors, Universal Robots, Turck Inc., and Red Lion. More information on our sponsors will be provided later on in this video. You can also find company and product information in the information section below. Our presenter today is Executive Editor of Control Magazine, Jim Montague.
For decades, industrial networking meant point-to-point hardwiring that carried analog current or voltage signals from a control room or other central location to each cabinet, I/O point, drive, motor, instrument, and sensor. These components sent signals back over similar dedicated pathways. However, as process applications grew larger and more complex, this led to overflowing cable trays and cabinets that looked like they were full of colorful spaghetti. Despite their difficulties, many networks like this, or portions of them, continue to operate today. Because of point-to-point networking costs and complexity, not to mention the sheer volume of wire it consumes, developers sought to have cables that can gather signals from more than one device at a time. This can be done by sending low-power impulses superimposed on a 4 to 20 milliamp continuous analog signal, or by using digital methods that slice data into tiny pieces delivered in a series. Either way, these analog and digital communications eventually progressed enough that multiple signals could travel over one, two, or several wires, much like the conversations that moved between telephones. As a result, one twisted paired cable can go from a distributed control system, programmable logic controller, or other master device, meander among participating components, and allow them all to communicate on the same looped circuit. This lets them send their data back to the controller and receive orders from it. While these innovations were often preceded by advances in telecommunications and computer networking, on the plant floor, this loop came to be known as a fieldbus because of the field devices it connected. While the basic fieldbus concept might seem cozy and collaborative, in practice there are many different communication protocols and standards, and they typically aren't able to talk to each other or allow their devices to interoperate. Although there has been some progress on translation and interoperability in recent years, they remain differentiated by communication speeds, data packet sizes, information organization, and physical media, usually because they grew up serving different technologies, industries, and regions, mostly in Europe, North America, and Asia. The other big snag is that suppliers of industrial networking devices and controls didn't want their products to interoperate because they feared losing market share. This is why the IEC 61158 fieldbus standard ended up with 8 heads, or fieldbus protocols it agreed to cover. Even the emergence and increasing dominance of Ethernet has failed to resolve this problem because there remain several major Ethernet flavors or protocol languages. As a result, many users still have a devil of a time getting their devices to communicate with each other. It's like everyone is on the same telephone line, but they're all speaking different languages. Increasing levels of microprocessing power and software have been thrown at this problem, and some cooperative efforts by networking trade organizations have helped, but many hurdles remain. Despite their differences, most of the field buses, their protocols, and other network methods fit into the 7 abstraction layer Open Systems Interconnection model developed by the International Organization for Standardization. Its 3 media layers include physical, for transmission and reception of raw bit streams over a physical medium; 2, data link, for reliable transmission of data frames between 2 nodes connected by a physical layer; 3, network, for structuring and managing a multi-node network including addressing, routing, and traffic control. Its 4 host layers include transport, for reliable transmission of data segments between points on a network, including segmentation, acknowledgement, and multiplexing; 5, session, for managing communication sessions such as continuous exchange of information in the form of multiple back-and-forth transmissions between 2 nodes; 6, presentation, for translation of data between a networking service and an application including character encoding, data compression, and encryption/decryption; and 7, application for high-level application programming interfaces, including resource sharing, remote file access, directory services, and virtual terminals. There used to be more field buses and proprietary protocols, but many have shaken out over the years. And though openness and Ethernet have expanded application types for each, they're still largely adopted according to historical precedent, namely, according to the process or discrete settings for which they were originally designed and support. The major remaining field bus types and their Ethernet versions include DeviceNet, ControlNet, and Ethernet IP, which are based on the upper-level Common Industrial Protocol and supported by the ODVA, Foundation Fieldbus H1, Foundation Fieldbus High-Speed Ethernet, and the HART Communication Protocol, which are supported by the Fieldcom Group, Modbus and Modbus TCP/IP, which are supported by the Modbus Organization, Profibus and Profinet, which are supported by PI International, and OPC and the OPCUA information sharing strategies that are supported by the OPC Foundation. As reported earlier, Ethernet, defined by the IEEE 802.3 standard, has made big gains on plant floors and in process applications, mainly due to its multi-gigabits per second communication speeds, the simplicity and low cost of its Cat5, 5e, and 6 cabling, and communication organizing strategies such as intelligent switching and organizing that let Ethernet avoid data collisions and behave more deterministically on the plant floor. These attributes have overcome the fact that Ethernet's flavors may not talk to each other, and because it's usually limited to 100-meter segments before a repeater or switch to fiber optic cabling is needed. When they can, many users skip the industrial protocols and use plain vanilla Ethernet, or its more technical name of Transfer Control Protocol / Internet Protocol, which can communicate more widely. Of course, the downside to all these added connections and links to wider networks and systems is more vulnerabilities and vectors for probes, intrusions, and attacks. This requires users to assess, monitor, and implement cybersecurity by enabling passwords and other basic protections, segmenting their networks with managed Ethernet switches used as firewalls between subnetworks, and monitoring their network traffic for anomalous behaviors. Ethernet's reach has been extended further with wireless Ethernet technologies based on Wi-Fi and its IEEE 802.11 standards, or other wireless techniques from short-distance Bluetooth to longer-distance radio, cellular, and satellite solutions. These technologies have benefited from the ongoing development of more cost-effective, capable, and rugged antennas, transmitters and receivers, wireless mesh and self-healing topologies, and more thorough site audits and installations by users. The other game-changing aspect of Ethernet is it allows users to implement IP-style networking methods and organizational strategies. This, in turn, is bringing many process control applications, their components, and their data onto internal intranets, the wider industrial Internet of Things, and onward up to cloud computing services for big data analysis and, hopefully, more informed decision-making by users. Once Ethernet touches the Internet, all of today's IIoT and Industry 4.0 activities begin to happen, but they're all rooted in the industrial networks that came earlier.
Thank you for watching the Control Design educational video series, Automation Basics, Industrial Networking. This video has been brought to you by our sponsors, Universal Robots, Turck Inc., and Redline. Universal Robots provides a robust development kit for secure custom networking applications. Multiple IIoT systems have already been developed through the UR Plus ecosystem, featuring plug-and-play products for UR cobots. UR products are compatible with Ethernet IP, Profinet, Modbus, and TCP/IP protocols, with room for custom communication implementations. Also benefit from a secure framework for reading out robot data for big data collection. With Turck's field logic controllers powered by ARGEE, engineers can add logic to compatible Ethernet I/O devices without a PLC, driving down the cost per I/O point and increasing flexibility and control. The easy-to-use programming environment can be accessed from any device and allows engineers to create device-level control without complex third-party software or licensing. Red Lion turn information into action anywhere, anytime with their industrial automation and networking solutions. Optimize real-time data visibility and OEE.